Hey guys, today we're going to be talking about carbohydrates. This is the first of the four macromolecules in biology. Macro means big or just really important. You can think of it as a very important molecule, but it's also a big molecule, okay, a lot bigger than water or other ions we will be talking about. So, carbohydrates, look at all these tasty snacks they give us, okay, all of these wonderful things like ice cream and muffins and bananas and potatoes. But more importantly, they have a lot of nutritional importance, and they have kind of a bad rap at the moment. And there could be good reason for that, depending on your health, etc. So if we were to look at the back of this package right now for these tasty carrots, you'll see total carbohydrates listed at 7 grams, but then underneath of that, you'll actually see it broken down between dietary fiber and total sugars. So both fiber and sugar are carbohydrates, but why do we break them down that way on packaging? I guess we'll find out. Here we go. All right, so carbohydrates, like I said, you've probably heard of them recently due to the low-carb diet fads. And the reason for this has to do with the way that we use carbohydrates to store energy in our muscles. And if you don't necessarily use that energy, that stored carbohydrate, then it can go into long-term storage, and that is going to be fat, all right? So carbohydrates, these are our primary energy molecules. These are the primary ways that we're going to do cellular respiration is through carbohydrates. So they're composed of CH and O. So what they're made of is actually in the name. So if you look at this, you have carbohydrate. So 8, that suffix means having the appearance of or looks like. So hydro means water. So this thing looks like water with a carbon slapped on there. And that's exactly what it is. Its function is pretty much energy or energy storage, and it can also be used as a raw material and a structural material, which we will come to, which kind of answers our fiber versus sugar question on the nutritional label. So its monomer is a sugar, so this is the first time we're kind of seeing this nomenclature here. Mer always means number, so this is going to refer to a number of something always in biology, and mono means one. So the monomer of carbohydrates is a sugar. So each one of these little guys here, you can see chained together, each one of these little hexagons is a sugar. So examples of sugars are going to be your starches, your cellulose, and things like that. The basic chemical formula for this is going to be CH2O. And you can see here, you can do it like this, CH2O inside of these parentheses with an X here, and that X represents the number of carbon molecules we see. So in the case of glucose, which is right here, if you were to put a 6 here and then factor this out, it would be C6. 6 times 2 is 12, and then you put the 6 here on our O. So this is just basically the general chemical makeup of a carbohydrate, and it can kind of vary from there, but that's kind of what we're usually looking at when we're talking about a sugar. So another really important language thing here is in all of biology, if you see the term ose, a suffix ose, that means you're looking at a sugar. So regardless of whether you know what it is or how complicated it is or how big and scary the word is, if you see ose, that means sugar. And we can classify these based on the number of carbons in them. So hexose, hex means 6. So glucose is a hexose, ribose is a pentose, and triose, this guy over here would be considered a triose, all right? So glucose you've seen before in cellular respiration. You've actually seen this guy before, I'm sure, in regular biology, ribose, okay? This is going to be one of the backbones of ribonucleic acid, all right? So 6, 5, and 3. So sugar structure. So I remember when I was learning this, I was very scared looking at these diagrams, and the reason for that is because I didn't understand that these were actually the same thing. The linear and ring forms were actually the same exact molecule, just one is kind of in a vacuum, what it would look like just floating around in space, and then the other one is actually what it looks like in biology, because biology is in water. So when it's in water, they tend to form these rings. So we were talking about how carbon, when you stick like 5 or 6 carbons together, you start to form these rings. Well, the same thing is happening with a sugar because it has this carbon backbone. All right, where do you find solutions? In biology, well, that's cells. Remember, 78 to 85% of a cell is going to be water. So our carbohydrates are going to be in this ring form. So this is something you've probably seen before in regular biology as well. You just didn't understand it when we were talking about the arrangement of DNA running 5' to 3' or 3' to 5'. You're probably like, why are we talking about this? I don't get it. The reason for that is because that's how we number our carbons in sugar, and it lets us talk about the structure that we're going to be making when we start sticking these sugars together to form more complicated molecules. So we always label them this way. So we start at the rightmost carbon, and then we label them going clockwise. So 1', 2', 3', 4', 5', and then 6' is out here hanging out by itself. So the reason I highlighted these 5 and 3, because guess what? That's how you're going to build something like DNA, so your nucleic acids. So here we go, back to the kind of scary language here. If you've ever heard the word saccharin, that means sweet, but it's referring to sugar, okay? It's from the Greek that means sugar, so saccharin. So once again, if we know what the words mean, a monosaccharide, it is one sugar. Okay, so that is the monomer. It's the fancy name for what the monomer is of a carbohydrate. Okay, it's a monosaccharide. So glucose here is the most simple carbohydrate. All right, so that's going to be a nice monosaccharide is glucose. Okay, a disaccharide is going to be 2 monosaccharides stuck together because di means 2. So sucrose, if you stick a glucose plus a fructose together, you get a sucrose, and that's table sugar. And then the really complicated guys, these are your polysaccharides. These are big, complicated molecules. Poly means a lot. Okay, this is one of the most fundamental, important things to understand in biology is dehydration synthesis. This is how we put together carbs, it's how we put together nucleic acids, and it's how we put together proteins. So please, please, please make sure you understand what this means. So carbohydrate, it's carbon and water, okay? So dehydration synthesis is where we actually remove some of that water from our carbohydrate. Okay, so we are dehydrating our carbohydrate to stick our simple monosaccharides together to make this disaccharide here. So if you look, you see this this hydroxyl group and you see this hydrogen here. If these two guys come together, well, they're going to form a bond and make water. And when they make water, that chemical reaction is going to allow this glucose and this glucose to stick together and make something like this, which is maltose, which is a disaccharide. Okay, we call those glycosidic linkages. I don't know how often you're really going to hear that term, so I wouldn't super worry about it. And the reason there's a picture of this not very good imported beer is because maltose is the primary sugar that gets fermented when you're actually making beer. All right, so dehydration synthesis. So here we have a glucose and a fructose. Okay, you notice that our structures are a little bit different here, okay, between our glucose and our fructose. All right. But same thing, when we stick those together, you have the exact same thing happening. You have this dehydration synthesis happening. So we're removing this hydroxyl and this hydrogen, and we are getting table sugar, which is sucrose. So by removing that water, when those two things come together, you can make these disaccharides. All right, so finally we come to polysaccharides. So these are polymers of sugars, okay? So once again, mer means number, poly means a lot. Okay, so when we say polysaccharide, we just mean a lot of sugars stuck together. Okay, so poly means a lot, mer means number. So when we say polymer, we're talking about a bunch of things stuck together. And when we say polysaccharide, specifically, we mean a bunch of sugars stuck together. All right, so a bunch of monosaccharides stuck together make a polysaccharide. So what's cool about these things is they don't really cost a lot of energy to put together, and when you break those bonds, it releases energy. And you already know this. This is how basically cell respiration works. This is why we eat food. So when we look at our nutrition label, like we do here on our carrots, all right, one of the things that it's listing is calories. But potentially we're not always using everything that we're eating just for the caloric value, just for energy burning. We can also store some of that, but we can also use it to actually build our bodies, because that was another thing that we said. So not only is there energy storage, there's also structural functions that carbohydrates can have. So in plants, the polysaccharide is generally going to be starch. The polysaccharide that we use is a really cool thing called glycogen. So when you go for a run, your body is initially going to use the glycogen stored in your muscles to actually power cellular respiration to get you through that run. Now, if you were running really, really fast, or maybe you rock climb like how I like to, you can get through that glycogen pretty quick, and you can end up in an anaerobic situation, and then you're no longer really using that glycogen, and you're relying on different metabolic processes to power your bodies. And we'll get into that later, but there's a lot of nutrition and sports science that's really cool when we're talking about something like this, like carbohydrates. So I said it's also used for structure, so it's used for cellulose in plants. So if we go back to my carrots here, what is cellulose? Well, that's the fiber part of this. So fiber is carbohydrates that we can't digest. We cannot digest cellulose, and these carrots are a vegetable, so they're going to be made of cellulose because that's what helps give plants their structure. That's what makes their cell walls. And then my favorite polysaccharide is chitin, which makes up the structure of arthropods and fungi. So our little fly amanita mushroom over there that will kill you if you eat it is made of chitin. This little bug here is made of chitin. This little lobster here is made of chitin. And I kind of think of this as the most metal looking of our polysaccharides. If you see here, like the hydroxyl group has been replaced by this acetylamine group, and it kind of is just metal looking. It's got these like spikes on it. I don't know. I just think it's kind of sweet. So I just think, like, when you see metal dudes with like spider tattoos and stuff, I just think it's kind of funny to think about the chitin that makes up that spider, that makes that dude feel like he's pretty hard with his spider tattoo. All right. So linear versus branched polysaccharides, this is extremely important. This is how we're going to store our simple monosaccharides. We stick them all together for storage. So starch here is how plants are going to be storing their polysaccharides. They do it two different ways. They do it through amylose, which makes this nice linear pattern here. Okay, these are going to be 1' to 4' linked, which makes this nice linear pattern. You can see it's just like how a rope is. And then they can also make this thing over here, amylopectin, which is still a starch. But if you look, you have this nice linear part, and then you get right here, and you see we have a 1' to 6' linkage, and that's going to create these nice branched patterns. All right. And then we can come to glycogen in us, which is a really, really awesome molecule. Like I said, this is what we're going to be using to power all of the movement that you're doing. And if your blood sugar drops, like if you're in a fasting state between meals, your liver has all the stored glycogen, and it starts to release that glycogen into your bloodstream to help keep you awake and moving. All right. This is the reason people carb load before they run marathons, is because they think it helps rebuild their glycogen stores. It's kind of mixed science there. I don't know. But anyway, if you look at glycogen, what's awesome about it is it has this incredibly complex branching pattern, and that basically allows a really fast release of the energy stored in there, because you can pack a lot of bonds really close together. So you drop some enzymes in here and bam, you are making ATP left and right, and you're powering your body. Whereas a plant is more interested in kind of a slow release of that energy, because it's going to store it in seeds and, maybe a potato, like an underground storage organ for hard times. Okay, so the molecular structure always determines function. That's common to all of biology. Structure determines function. So if you look here, basically you can have an alpha glucose and a beta glucose, and the difference there is where the hydroxyl group is. So whether it is below our first carbon, or whether it's above our first carbon, and that's going to actually make the difference between some pretty important molecules here. All right, so that difference right there, this gives us starch. If you stick a bunch of these together, you stick a bunch of these together, now you have cellulose, which we can't digest. So if you kind of look at the difference here, starch is really easy to digest. It has this very simple pattern. It's all the same back and forth like that. But if you look here at cellulose, the way our beta glucose monomers stick together is they actually have this flipping pattern. So right here you can see this hydroxyl, and now it's up here, then it's down here, then it's up here, and that's going to make a very strong molecule that we can't digest. We don't have enzymes for it. All right. So when you hear the word ACE, like lactase, that is an enzyme for digesting lactose. Okay, so we don't have cellulase. We just don't have it. All right, so cellulose is the most abundant organic compound on Earth. You stick this stuff underground for a couple million years, and eventually you might end up with something like coal or oil. All right, it's very energy rich, and it's the most abundant compound, organic compound on Earth, because it helps make up the cell walls of plants. Okay, most carnivores do not have cellulase at all. All right. So cellulose, it's the same thing as fiber. Okay. So cows, they do have, they don't technically have cellulase, but they have bacteria that lives inside of them that lets them digest that. Whereas a gorilla, who's also eating a lot of plants, they need to also eat fruit and stuff like that, because they can't actually get any energy out of the cellulose in those plant leaves. Whereas a cow's totally happy just eating grass all day, which is disgusting. And that's all due to these really cool symbiotic relationships that cows have with bacteria. Termites, the reason they are so dangerous to have in your house is because they also have bacteria that live inside of them that can digest cellulose. So they can break down wood as food. Okay, you've never seen a human get really hungry and want a snack and go start chewing on a tree, and it's because we don't have the enzymes to break down cellulose. Whereas a termite's like, hey, that tree, that's a tasty looking snack. Okay, and that's simply due to these really cool symbiotic relationships. So the bacteria do have it, and they can basically start breaking down those bonds, and then then the cow can take that beta glucose, now that it's broken apart, and do cellular respiration with it, just how we would if we were to go, eat a Snickers. All right, so that's a pretty quick overview of what's going on with carbohydrates. Like I said, this is extremely important because it relates to nutrition science, it relates to diets and why certain diets become fads and don't become fads. It relates to sports science, which is why I think it's very interesting. But more than that, carbohydrates actually help build the structure of us and plants and fungi, which is something we really don't think about. We think about the energy releasing qualities and the energy storage capacity of carbohydrates, but we don't think about the fact that they actually help build up bodies, and they can make really complex things like lignin, which helps plants stand up. All right. Or cellulose, which also just builds the cell walls for plants, and it's pretty cool. Okay, guys, so that's all I got for you today. Stay curious. Thanks a lot. I appreciate it. Go eat some carbohydrates. All right, bye.